Hello friends, welcome back to this video channel. My name is Dr. Sujit Kumbar, working as Assistant Professor, Automation and Robotics Department, Sharad Institute of Technology College of Engineering, Edra, Karanji. In the previous video lecture, we have seen the basics of stress and strain. So in this video lecture, we will see types of strain. So strain is defined as it is a change in dimension to original dimension. So strains are classified as lateral strains or linear strain on the basis of the direction. So first we will see what is linear strain. So linear strain of a deformed body can be defined as the ratio of change in length of the body due to the deformation to its original length in the direction of force. In the given figure, the force is applied, it may be tensile or compressive, in the direction of its axis. So change in length upon original length can be considered as linear strain. Lateral strain. Lateral strain of a deformed body is defined as the ratio of change in length which is perpendicular to the dimension of the body to its original length. Now, in the given figure, the diameter is changing. It's a circular rod where the P force is applied, due to which the diameter is changed. So, the ratio of change in diameter to original dimension is nothing but lateral strain. The students are advised to remember that the lateral strain is defined as the ratio of change in dimension which are perpendicular to the applied force. Elastic and elasticity and elastic limit. Most of the engineering materials are ductile in nature. When the external force is applied on the body, it undergoes some deformation. And if the body regain its original position and shape, when there is a complete removal of load, then it is called as elastic body. And the property of a material by which it returns back to its original position, that is shape and size, on the removal of external force, then that property is known as elasticity. This property plays very important role in automation and robotics. The elastic limit is that value of stress up to and within which the material returns back to the original position, that is its shape and size, on the removal of external force. If the value of external force is such that it exceeds the elastic limit, then the body will not completely regain its original position. It means that elastic limit is the extreme limit of the body where it regained its original position. After elastic limit, that body falls into plastic region. So an example is shown here. There is a metal rod, that is hanging metal rod of 2 meter length. When the weight is attached there, then there is a extension of the rod takes place. Therefore, the stress induced in that material can be given by the formula F upon A, where F is the total weight of the body that can be converted into Newton. The elastic limit is the maximum stress of a body that can experience without becoming permanently deformation. In figure number B and figure number C, there is no any problem, but after certain limit, that is elastic limit, the length of that particular rod will not regain its original position, that is it will not be 2 meter after removal of load. So that is the example of elastic limit. Hooke's law. Hooke's law states that when a material is loaded within elastic limit, stress is directly proportional to strain. In the figure of stress strain diagram, we will learn that stress strain diagram in this video lecture later on. So OA represents elastic limit. So within elastic limits, stress is proportional to strain. As the stress changes, strain also changes. So at the right hand portion, stress is directly proportional to strain. And in order to remove that proportionality sign, we have to add proportionality constant. Capital E is the proportionality constant and capital E is equal to sigma upon epsilon. That is sigma is the stress and epsilon is the strain. The modulus of elasticity is the slope of the stress strain diagram in the linearly elastic constant. So, area under the curve OA represents Hooke's law, and the equation for Hooke's law is sigma is equal to E into epsilon. Elastic constant and their relationship. When an elastic body is subjected to stress, a proportionate amount of stress is produced. The ratio of applied stresses to strain generated always be constant, and it is also known as elastic constant. So there are various elastic constants. First of all, Young's modulus of elasticity. We have already discussed this in previous video lecture. Second one is the bulk modulus. Third one is the modulus of rigidity. And fourth is the Poisson's ratio. First, we will see Young's modulus. This part we have already learned in the first video lecture. So, according to Hooke's law, when a body is subjected to tensile stress or compressive stress, the stress applied is directly proportional to strain within elastic limit of the body. The ratio of applied stress to strain is constant, and that constant is known as Young's modulus of elasticity. So see, this Young's modulus terminology is very very important in design field. So E for different material is different. Young's modulus is denoted by letter capital E. And how to determine capital E? For that purpose, you must know stress value and strain value. How to determine stress? Stress is equal to internal resistive force upon area. Strain is equal to change in length upon original length. So from this, you can easily calculate Young's modulus of elasticity. The unit for Young's modulus of elasticity will remain same as that of stress, as strain will not have any unit, it's a unitless. Next terminology is bulk modulus. One example is shown. When a body is subjected to mutually perpendicular direct stresses which are alike and equal within its elastic limit, the ratio of direct stress to the corresponding volumetric strain found to be constant, and that is known as bulk modulus of elasticity. In simple word, you can define bulk modulus as it is a ratio of direct stress upon volumetric strain. How to determine bulk modulus? Bulk modulus is equal to direct stress. As the area remains same, you can consider delta P, change in that force, divided by volumetric strain, that is delta V upon V, change in volume upon original volume. Bulk modulus, rigidity. When a body is subjected to shear stress, the shape of the body gets changed. One example is shown here, as it is a cuboidal body. So the force is applied, equal and opposite force are applied at the edges, so that deformation takes place. And here the rigidity modulus or modulus of rigidity can be defined as it is a ratio of shear stress upon shear strain. And the notation for rigidity modulus or modulus of rigidity is different in different book. In some book it is given by letter capital G, C or N, and unit of modulus of rigidity is again same as that of shear stress, that is Newton per mm square or megapascal. Next terminology is Poisson's ratio. Within elastic limit, the ratio of lateral strain to longitudinal strain is known as Poisson's ratio. Poisson's ratio is maximum for ideal elastic incompressible material, and its value is 0.5. For most of the engineering materials, Poisson's ratio lies in between 0.25 to 0.33. Poisson's ratio, as it is a ratio of lateral strain to linear strain, it has no unit. One example is shown here. It's a cylindrical rod where force is applied axially. So linear strain means it is the ratio of change in dimension along the direction of applied force, and lateral strain means perpendicular to the direction of applied force. Diameter will change, so perpendicular to the applied force, therefore delta D upon D is nothing but lateral strain, and as the length will change along the direction of applied force, so delta L upon L will be linear strain. Relationship between elastic constants. So in examination they may ask to find out Young's modulus for different material. If the Poisson's ratio is given or modulus of rigidity is given. So there are some relationship between Young's modulus, modulus of rigidity, and Poisson's ratio, and it can be expressed as capital E, that is Young's modulus of elasticity is equal to 2 times modulus of rigidity into bracket 1 plus Poisson's ratio. Similarly, the relationship between Young's modulus, bulk modulus, and Poisson's ratio can be expressed as Young's modulus E is equal to 3 times K, that is bulk modulus, into 1 minus 2 times Poisson's ratio. Factor of safety. This terminology is very important. Factor of safety is the ratio of ultimate strength of a member or a piece of material, such as in the case of aeroplane, such as arm of the robot, to the actual working stress or the maximum permissible stress when it is in use. In simple word, the factor of safety is equal to ultimate stress to working stress. That is load that breaks the product divided by normal load on the product. For example, if a robotic arm is working normally under the load of 100 Newton, but when the load of 4000 Newton is applied, at that time that robotic arm will simply break. So factor of safety is equal to the load that breaks the product or ultimate stress to working stress, that is 4000 Newton divided by 1000 Newton, 4 by 1, that is factor of safety is equal to 4. While designing any component, the factor of safety must be greater than unity. I hope you have learned all these important concepts. So in the next video lecture, we will see the stress strain diagram for ductile material. Thank you very much.